Okay, can we start now?
I'm not sorry for it.
Can we start? Can we start?
Yes.
Okay, so now the other method which we are going to discuss is conjugate beam method. Okay, conjugate beam method is similar to, is actually derived from the moment area method. It's using the same logic, but the way the genesis is different. The way it is derived, that's different. And based on conjugate, like conjugate beam means that you develop a fictitious beam and you try to find out a deflection. Conjugate beam meaning that it's not real, it's a fictitious beam. Now how does it work? In order to understand the conjugate beam method, you have to understand these relations. Now this is familiar to you all, okay? What is EIY? That's a deflection, isn't it? Yeah? You differentiate that, you get a slope, don't you? EI dy by dx is slope. You differentiate it once more and you get EI d2y by dx square is equal to moment. We have derived this equation, haven't we? Yes? So this is moment. Now if you differentiate the moment, dm by dx, that's shear. Okay, so in other words, EI d cube y by dx cube is shear. And if you differentiate the shear, you get the load. Agreed?
Yes.
So this is familiar to you. Yeah? It is familiar? Now look at the relationship. Now we have to develop an analogy. Okay? How do we develop that? You have a beam, for example, which is subject to some loading. Yes? How do you find out? So you are over here. What is shear? How do you find out shear? All the forces which are towards the left. That's based on our sign convention. So that is shear. So if I want to find out shear anywhere in this beam, I'll take a point and find out the forces, the net force at the left, or in other words, summation of all the forces to the left. That's my shear, isn't it? So you can take it right, but our sign convention, you can take the right direction also, but normally we take the left direction. So towards the left, you sum up all the forces and you get shear, don't you?
Yes.
So from load, you can come to shear. Agreed? And any confusion? Now, once I find out my shear, from shear I can find the moment. So it is, what is moment? Summation of, what is that? Summation of moment cos, no, summation, yeah, area, it's also area, but it's also summation of the moment caused by all the forces which are, say, towards the left at a particular point of interest. Okay, so that is our, so these three are connected, isn't it? Load, you find out shear, yeah, and you find out moment. Yeah, they are connected via your differential equation using these equations. Okay, so in other words, the load is connected to your shear, to the differential, the first differential of shear. The shear is connected to your moment because it's the first differential of your moment, and moment is m. Okay, so that's how your these three items are connected. So analogously, if we say that we take a moment diagram, now how, okay, before that, these three are connected using the logic of moments or forces towards the left, okay, and differentiation wise they are connected over here. Okay, so if you integrate it once, you integrate the load once, you get shear. You integrate it again, you get moment. Okay, now look at this one. If I start from the moment, and integrate it once, I get slope, and I integrate it again, I get deflection. So these three are also connected similarly, aren't they?
Yes.
I mean, mechanics wise, or in other words, mathematically these three are also connected, similar to this one.
Sir,
These
all five
differentially.
are same relation.
Sorry?
Sir, they all five are connected in the same relation.
Yes, but I'm saying you take these three first, okay? How do you find out? From load, we find out shear, and from shear, we find out moment.
Yes.
Okay? There is a connection between these, all three of them. And how are they connected? You have got the first differential, you integrate this, okay? So your load is dV by dx, okay? Then your shear is dm by dx, and this is m, yeah? So mathematically they are connected. These three equations are connected, and the method we use to find out shears and moment, that is by taking forces at the left, okay? And either we find out shear or either we find out moment. Now look at these three. This is a moment, and mathematically they are connected the same way as these three.
Yes, sir.
Agreed?
Yes,
These
sir.
three are, because we have got d2y by dx, yeah, integrated, you get dy by dx, and integrated, you get the deflection. So, can't we use, so if we have this thing satisfied, this thing is satisfied in these three, so we can also say analogously that we can use the same method as this one, finding forces at the left, and we can find out the slope and deflection. What do I mean? I mean that if I load my beam with the bending moments, yeah, I load my beam with bending moments, find out and then treat that as a load. The bending moment diagram, I treat that as a load on the beam, and at a particular point, if I find out my shear, that will be actually equal to slope.
Yes, sir.
And if I find out my moments, that will be equal to deflection. Do you understand my point? So, how can I say that? Because I developed that logic from these three parameters, the connectivity between these three items. Okay, do you understand my point?
Yes, sir.
So, in other words, if I have imagine I have the same beam. Yes, I've got the same beam, which is this one, and I draw the bending moment diagram for this. Okay, so let's before discussing cantilever, let us I have a yes, this is my bending moment diagram by parts. Okay, I pick it up and I load this beam with this diagram. So, what would be my reaction? What would be my reaction? I've got a beam which is subject to these two U beams. So you find out half 300 into 3. Yes? No, you have to find out the reaction. So you take either moment or you apply it as a concentrated flow. Okay, so this concentrated flow is at a distance 1 meter. How much is this? Half into 300 into 3 is equal to 450. Huh? 450 by EI. We have to draw M over EI. Okay, remember, EI is from here. So this is 450 over EI, or let me put the M over EI. And how much is this one? Half into 300 into 1 is equal to this one is at a distance 1 meter and this one is at a distance 1 by 3 meter. Yes. Now we can find out the reaction R1. R1 is equal to okay, so that is your R1. How much? 403. And if you check your previous answer, theta A was 400 over 3 EI. Remember? So that is your R1. So R1 is shear. So what is that? R1 is reaction, which is look at this one. Shear is analogous to slope. So this is your slope. That is the slope at A. R1 is a reaction. No, this is, imagine you have got two triangular nodes. How are you going to find out your reaction? So I've just found my reaction, that's it. Summation of moment at this point is equal to 0. So this is summation of moment at C is equal to 0. Okay? And similarly, you can find shear at any location. Okay? And that will give you the rotation. That will be the relative rotation between. So that will be the rotation. Okay? Or in other words, the rotation of the elastic curve. Okay? What does that mean? Which rotation are we talking about? If you have a tangent like this,
Then the arm you are taking for movement.
with respect to x, how much is that inclined? This is not a tangential deviation. The moment area method rotation is different. Moment area method rotation is actually the rotation, the relative rotation between two tangents at two particular points. Yes.
So this moment arm that you are taking, 450 over EI into 1. So this is not 1, sir. It should be 2.
What is the दूसरी side में moment लिया?
R1 taking
R1 times 3. And this time, this, how much is this from here?
Yes, sir.
Okay, so that is R1. And if you want to find out deflection at 1, how can you do that? At 1 meter from here. Deflection at 1 meter using conjugate beam method. How can you do that? How can you do that? When x is equal to 1 meter, how can I find out deflection at 1 meter from here? How can I find out my deflection? Look, I'll repeat. When I say deflection, deflection means it's analogous to moment. What we are doing is we are taking the bending moment diagram and we are loading it on the beam. Okay, we subject the beam to the bending moment diagram and then find out. If you are interested in finding out slope of the curve, this curve has got a slope, hasn't it? If you are interested in finding out slope of the curve at any point, what you do is you find out shear at that point. Just forget about everything. This is now the beam, okay? And you are asked to find out deflection, for example, using conjugate beam method. What do? You take the bending moment diagram, place it on the beam, okay, and then forget about your shears and your deflections and slope. Only thing you should remember is that the reference point where the slope is required, you find out shear at that point, and the reference point where deflection is required, you find out moment at that point. So it's the simple problem, okay, but it has got a bit involved loading, and you just find out either the shear at that point or moment at that point, and that will be equal to your slope or deflection. So if you are trying to find out deflection at 1 meter from here.
Multiply the area by
What do you mean? Multiply
Sir,
the area
you
by
can
1.
find that area that is load, and then you multiply it by 1, that is the distance.
No, you just try. Look, don't go into area or anything. You just find out moment at that point. That's it.
Moment to the left.
This is the point. Just find out there is a shear and there is a moment. Isn't it?
Yes,
Just
sir.
find out moment at this point. So, what is this moment? This moment will be equal to. So, moment at B is equal to. How much is, first of all, find the magnitude. How much is this one? 300. This is 100. Okay? So this is 100. So, and B is equal to R1 times 1. That's how we find out our moments, don't we?
Yes, sir.
Okay. And B is equal to R1 times 1 minus, this is like this, and yes, this is plus and half into 100 by EI into 1 by 3, isn't it? That is the, and R1, so R1 is 400 plus 100 by 6 EI.
900 over 6 years. 150 over year. 150 over year.
Okay. This R1 is in which direction?
Upward direction.
No, this is downward direction. Because, look, this is upward and this is small one which is downward. So this R1 is in this direction. Okay, so
This will be equals to tiny change over here.
sorry.
Yes, sir, minus that. Yes, sir.
Minus R1 के साथ है.
Sorry.
116.67.
And it is similar to
Yes, sir.
what we had previously.
Yes, sir.
Okay, so
Negative R1 के साथ
however you want to take it.
सर एंटी क्लॉकवाइज आप जब भी बोल दिया नेगेटिव इसमें ऐसे बहुत सारी है
Yes, but you take it other way around.
सर अभी तो आपने इक्वेशन लिखी है, वहाँ पर नेगेटिव सर आने चाहिए R1 के साथ.
वरना ये सर इक्वेशन सही थी वो मोमेंट इधर नेगेटिव से उधर जाके पॉजिटिव.
Okay, but however you want to take it, it doesn't matter. Okay, sign convention doesn't matter. The thing is, how do you know? The question is, how do you know R1 times this one? Okay, that is going So, using our sign convention, we can have this minus and this one as plus. Okay, so this is minus, this one as plus, and how? And this is negative 116.67. Okay, now what does this negative 116.67 mean? What is the direction of deflection? Under this load, deflection should be in this direction. Yes, and sorry?
So the deflection would be of the opposite direction of that of the load.
No. This is the same direction, but what is the logic? It's the same direction.
So the load in this case.
Sorry? No, the load is, yes, the load is in this direction. But we are not talking, this is with respect to this one. This problem. This problem has got deflection which is coming like this. Okay? So, we have this load as positive and this load is negative. We treat this as negative. Yes? So if this is positive, then the moment which is caused, what should that be? That is negative. Moment by this reaction is negative, isn't it?
Yes, sir.
Okay? So from this equation, we are saying that actually the deflection is upward. Okay, when we put it over here, deflection is upward. But we are getting negative, which means that it's not upward, it is downward. Do you understand my point? Okay, so using this logic, we are saying that a deflection is upward. That's what we are assuming. Okay, but you get negative, which means that the deflection is not upward, it is downward. And so you have to correlate your moment with the deflection. Do you understand my point? So moment and deflection, they are analogous. So you correlate. Okay, is this okay?
Yes.
Should I rub it off?
Thank you, sir.
The thing is, we have to finish the course. So,
How much was
okay, now what we did was for a simply supported beam. Okay, in a simply supported beam, you have got two hinge supports. Agreed? You have got two supports which are, one is a hinge and one is pinned. Okay, so in your fictitious beam, you should be able to find out your shear and moments in your fictitious. In other words, I mean that at point A, you have shear. Do you have shear?
Yes, sir.
And your moment is 0. So analogously, you should have slope at point A and the deflection must be 0. Okay, so you don't need to worry about point A. And similar is true for point C. Okay, but what if I have a fixed, a cantilever beam? If I have got a cantilever beam which is subject to subloading. I am asked to find out deflection at these points. Deflection at A. How can I do that? I have to draw the bending moment diagram, isn't it? So what is my bending moment diagram? How should I draw it? This is my bending moment diagram, isn't it? This is my bending moment diagram. Agreed? This is BMP. Now I take the same beam and load it by this bending moment diagram. Okay, the same beam is loaded. Now the thing is, at B, I've got a fixed time. Agreed? At B, I've got a fixed time. So, what does that mean? No slope and no deflection. Or in other words, my shear and moment should be 0 at this point, isn't it?
Yes, sir.
My shear and moment should be 0 at point B. But if I load it like this and use B as fixed, my shear and moment won't be 0. At point A is free. So my slope is finite. My shear is finite. Sorry, my deflection is finite. I would have a finite deflection and finite slope at A, isn't it?
Yes, sir.
So, what does that mean? But in reality, over here, in this case, in the given case, my A is free. So, the shear and moment are, what is shear and moment at A? What is shear at A? At free end, what is the shear? And at free end, what's the moment? 0. Look, what I'm saying is, huh?
Bending moment at B. No, sir, it's not.
What are you talking about? Look at this.
Yes, sir, yes.
I've got load P over here. So, this is my bending moment diagram. And what is my shear? Yeah, depends on whatever our direction is. Okay? So if I am asked to find out deflection, for example, at A, deflection is analogous to slope. Okay? So I can't use the same support conditions to find out my deflection. Why? Because the moment at A is 0. If I put this thing over here and keep B as fixed, so the moment at A will always be 0, isn't it? Do you understand my point? Do you understand that the moment at A would always be 0? If I treat this as a load and apply it, so what should I do? How can I overcome that? What is that support which will give me moment? So I make this fixed and this one free. if I make this one fixed, point A fixed and point B free, what will happen is that I would have finite moment at this point. Okay? I would have finite moment at this point, won't I? And I would have zero moment at this point. Okay? So having finite moment means that there would be a deflection at this point. And having zero moment over here would mean that I would have a zero deflection, which is true in this case. So my point is that in the case of cantilever, what you have to do is you have to make free fix and fix free. And the logic is what you have to make sure that if you have finite, if you want a finite deflection at a point, you must have a finite moment. If you want to have a finite slope at a point, you must have a finite shear at that point. If your slope, if your deflection is zero at a particular point, you should adjust your support in such a way that your moment is zero at that particular point. Do you understand my point? So that's what, so in the case of cantilever, the only thing you have to do is change the support. So that is your conjugate beam method. Okay, so I'll give you a 5 minutes break. Okay, another 5 minutes break, and then we will start with unit programming. Okay? Sorry?
Friday को भी class है आपका?
Yes, we have, but we have many methods remaining. Friday को
हाँ नहीं आ रही सर, बहुत ज़्यादा कॉन्सेप्ट इकट्ठे देंगे तो समझ नहीं आएगी।